So in this lesson, we are going to learn about some of the important properties of liquids, and we're also going to see how temperature and kinetic molecular theory apply to properties of liquids as well as the properties of gases that we just studied. So kinetic molecular theory, KMT, does describe liquids as well. And sorry about that. Come on, why is this not? Sorry about this. This computer is weird. It doesn't go back where I want it to go. That's not where I want to be. There we go. All right. Whew. It took me a little bit longer than I wanted to get back here. All right. So one of the important things, remember, kinetic molecular theory tells us that the average kinetic energy of a sample goes up. As that goes up, the temperature goes up. The speed of the particles goes up. And basically, liquids have more energy than solids. So we'll get back to solids tomorrow or in the next lesson. But if you think about a solid, the particles are all tightly compressed together. And as they speed up, they need more room to move. And we will talk more about this when we talk about phase changes in a couple of lessons from now. So particles, as they speed up and they move, they do come apart, and that gives liquids a few of the important properties that they overcome intermolecular forces, and they can do things that solids can't do. One of the things is flow. So you're all familiar with liquids flowing. When you pour water from one container to another, the particles flow. And what that is, the particles are able to move past each other. So in a liquid, they're held enough kinetic energy to hold the particles partially together. And because they're partially together, they have an indefinite shape. We like to say that they can take the shape of the container, but the indefinite shape means that there's no rigid structure. So we saw that crystal structure when we looked at ionic compounds, and when we looked at covalent compounds and how they form molecular compounds, molecular crystals. There's no crystal structure here. In fact, oops, I see the word random right there. I'm getting ahead of myself. Random structure. This random structure means that they are disordered. And this is going to be the first time we're starting to look at the concept of order and disorder. And as the temperature gets higher, things do become more disordered. And that disorder in a liquid becomes evident as having no long-range pattern, unlike solids where we have this repeating pattern of particles. Now, all materials, solids, liquids, and even gases we saw, all materials do this. There's a thermal expansion. What that means is as the temperature increases, the volume increases because the particles have more energy. As we said above, they need more room to move. So the material expands, and as the volume goes up, remember density is equal to mass over volume. As the volume goes up, so the numerator is going up, for a given mass, the density is going to go down. And so for most materials, water being a notable exception, we always see across all temperatures that the volume is going to go up as the temperature goes up and the density will go down. Another important property of materials, of liquids, is viscosity. So liquids flow. Viscosity is the resistance to flow. And you can think of things like maple syrup, honey, tar, molasses is another one. Things that you can think of that hold together very tightly. And this resistance to flow depends on the strength of the IMFs, the intermolecular forces. So high viscosity is an indication of high intermolecular forces, and it goes back the other way as well. So let me redo that double-headed arrow. So high intermolecular forces give high viscosity. And things like maple syrup and honey and molasses have sugar in them. And sugar has many OH bonds. And so sugars and these kinds of liquids form a lot of hydrogen bonding. And this hydrogen bonding holds things together very well. Tar is, like we saw yesterday or in the previous lesson, with the hexane versus the methane, more carbons in a chain, the stronger the force of attraction between them. And so tar has some really long chain carbon molecules, and those long chain carbon molecules hold together really tightly. Now, we've talked about boiling point as an indication of intermolecular forces and how boiling point indicates the strength of the intermolecular forces. And when you do boil, and we'll talk about this again in phase changes, you overcome the intermolecular forces and allow the liquid to come into become a gas. But before you get to that point, you can overcome the intermolecular forces in viscous liquids by increasing the temperature. And if you think about it, if you've ever tried to make your make your syrup flow a little bit easier or make the honey move a little faster, I don't know anybody who actually uses molasses, but maybe you do. You heat it up and it makes it flow a little easier, a little faster. And side benefit is that it does make it taste better as well. So more kinetic energy, we can overcome those intermolecular forces. And this is going to be a common theme. Getting enough energy, kinetic energy into a substance to overcome the intermolecular forces. So as the temperature goes up, the viscosity goes down. Increasing temperature, viscosity goes down. Another very important property of liquids is something called surface tension. Surface tension happens because there is an increased attraction between the molecules at the surface, as surface tension implies. So what happens here is this. If you look down in this diagram down below, in the main part of the liquid, we call the bulk of the liquid, where molecules are surrounded by molecules on all sides. So we have IMFs on all sides. At the surface, we're missing intermolecular forces up above the surface. And so what happens is the forces between the particles at the surface have to be extra strong. Increased attraction, as I said up here, increased attraction between those molecules, making up for missing atoms. And what the surface tension is, because surface tension does require increased energy, the liquid tries to reduce the surface area, and we'll talk about that in a few moments. For these for the surface tension, as with other things, higher intermolecular forces equal higher surface tension. And let's see, do I have it down below talking about temperature? That's one thing I don't have. So increased temperature can also, sorry about that. One of these days I'm going to figure out how to make this thing not jump around. And where do we want to put this? So increased temperature will decrease the surface tension of a system. Now, surface tension is one of a class of adhesive, or I'm sorry, not adhesive, cohesive forces, or forces of cohesion, in which we're looking at a force of attraction between two molecules of the same type. And that says it down below as well. So we're looking at cohesive forces, or forces of cohesion, two molecules of the same type that are attracted to each other. And this happens in all materials, and is stronger when you have higher intermolecular forces, and again will decrease as temperature goes up. If we want to break that surface tension, we can put in some soap. What soap does is soap gets in between the hydrogen bonding of water molecules. So if you picture water molecules up above, suppose each of these is water molecules, what you can do is put soap in. And soap is this strange structure. I'm not going to bother you with the structure. I don't want you to worry about what the structure is. But essentially, soap will get inside here. So soap gets inside there, and it breaks the surface tension. And this is why soap allows things to wet. What a material does when it coats the surface, it wets the surface, and we'll talk about that in a moment. And it allows wetting. It also allows or dissolves nonpolar materials such as grease and other substances that otherwise would not allow water to dissolve it. Now, if you were to take a water drop into zero gravity, like go up onto the space station, and you have a water drop up in space, the drops of water are going to form spheres. And you may have seen this. It doesn't matter how big. I say drops, but they actually use a fair amount. I've seen the astronauts use, say, a liter or so of water. They form spheres because what's going on in this space station when you're in zero gravity, now I'm not talking about in the vacuum, but when you're in zero gravity, what happens is if you have this water, the surface tension is pulling in. And so the surface tension is pulling in equally. And because it pulls in equally, it forms this sphere. And in a sphere, we have the lowest area. So surface tension depends on area, lowest area for any volume. This is why bubbles, you blow bubbles, it's going to form spheres. Anything that's left on its own is going to form spheres. On Earth, we don't have spheres because gravity is pulling in. And what happens is the water drops will try to form as close to a spherical substance as they can. And what they do is they will, it depends on what kind of surface they're on. If we're on a waxed surface, so say you have a car that's freshly waxed, what's going to happen is there's going to be a low attraction. And we'll get to this again on the next page. Low attraction to the water molecules, but the water molecules, we have the surface tension holding together, and it tries to form a sphere. But gravity pulls it down. This is not wetting. This particular surface, I'm going to write it up above, this surface is a non-wetting surface. And we call this kind of a surface hydrophobic. And we'll see more about the hydrophobic. See more about this on the next page. Okay, so a hydrophobic surface occurs when the water molecules, I didn't mean to do that, so the water molecule is stronger, the water molecules have a stronger attraction to each other. Let me write that. is at each other than to the surface. One of the things I want to make clear is that there are no repulsive forces going on. You often hear people say, oh, the wax surface repels the water. That's not what's going on. Water is still attracted. And this is kind of like what happens between oil and water, which we'll talk about in the lab in class. We will have talked about in the lab in class already. So what happens on a clean surface or a wax surface is we get that hydrophobic bubble. On a dirty surface, what happens is, and it's on the right, so this would be like a dirty surface. We get strong adhesive forces. What's an adhesive force? Let's scroll down a little bit and then we'll come back up. An adhesive force, force of adhesion, is attraction between two different kinds of molecules. So the surface of the material, and the water be two different materials. Strong adhesive forces, weak cohesive forces. This is wetting. And wetting occurs on what we call a hydrophilic, a Greek word meaning water-loving, hydrophilic surface. And you know the hydrophilic surface because basically the water is spreading out. It's being attracted down to the surface, and so it spreads out. It is being held together. We do still have surface tension in here. So there is still some surface tension holding this together. But the attractive forces to the surface are more important here. On the left, we have that hydrophobic surface again, the same thing we saw above. Hydrophobic, think word that means water fearing or water hating. Now, it doesn't really fear or hate water, but basically what's happening here is all around, and they don't show it here, but all around the water is pulling in. So we have stronger cohesive forces. The forces pulling that water together are trying to get this water to be as close to a sphere as possible, but gravity is pulling us down. Now, I just want to take one quick aside, and that is to talk about what the shape of a raindrop is, because I'd like to blow your mind a little here. So we usually draw a raindrop. Usually raindrops drawn like this. And I'm going to put a question mark on there because I want to try to convince you that that's not the shape of a raindrop. So think about what's going on here. The water is trying to form a sphere, but there's something that's pulling it up here. So something must be pulling up and something must be pulling down. What's pulling down is gravity, and so we know gravity is always acting. But what's pulling up is something else. So this would be the shape of a water drop if it's hanging off of a branch or something. This is not a raindrop. This is a hanging water drop. And you have seen this. You've seen these hanging off of branches. And this is why people think that raindrops are shaped that way. But I'm going to try to convince you that raindrops have to be another shape. So as the water drop is falling, if it was falling without any air around, a water drop falling would be spherical. So it starts off as being spherical. Now, what's happening as the water drop falls, let's label this a drop of water. As the water drop falls, gravity is pulling it down. But what ends up happening is because we're in an atmosphere, what ends up happening is the air resistance pushes up. And so what ends up happening is that the shape of the raindrop is not spherical. It's not that nice dangly shape. But what happens is the raindrop becomes this oblong kind of shape, almost like a bean, where it's being pulled down by gravity, but the wind resistance, the air, is pushing up and giving it this weird shape. So raindrops don't have the shape you think they do at all. And you can actually look this up and see that I'm telling you the truth. That's the shape of a raindrop. Pretty cool, huh? See, chemistry can tell you things that might surprise you. All right, so we've got this concept of adhesive and cohesive forces and wetting surfaces. These strong adhesive forces are going to allow a liquid to wet a surface, and weak adhesive forces are going to prevent wetting of the surface. And so we can look at the meniscus formed by two different liquids in a test tube to see how that works. With water, water has strong adhesive forces to the glass. Glass is made up of SiO2, silicon dioxide or silica. So we have SiO2 here. Now, in SiO2, I'm not sure if this is going to show up. Let me try a different color. These red molecules, red atoms, those are all oxygen. And these guys here, these are water molecules with oxygen, and the little blue circles, those are the hydrogen. Now, remember what we talked about the other day with hydrogen bonding. If we have hydrogen bonded to an oxygen, and so let me circle that. What color should I use? Let's use this color. So we have the hydrogen bonded to an oxygen, and then that hydrogen is attracted to the oxygen on the silicon. That's hydrogen bonding. And hydrogen bonding, if you remember, is very strong. And so we have hydrogen bond forces attract the water molecule to the container. The water is attracted because glass is also polar. And again, it has that oxygen for hydrogen bonding. And what happens when the water molecules are attracted is they wet the surface. And so they get pulled up. And they wet the surface on the inside. So what's happening on the inside of the container, on the inside of that beaker or test tube, is that the water molecules are being pulled up. Now, capillary action is an extreme about this. Now, as you're wetting, you also have surface tension because you're still going to have those water molecules trying to hold together. So we still have surface tension holding those water molecules together and trying to minimize the surface of the water. You don't want to make that surface too big. So what happens in capillary action is the liquid gets pulled up due to the adhesive forces. So in capillary action, the outer part pulls up. So let's draw a little diagram here. So if we start off like this, we pull up, but then in the middle, because we want to minimize the surface tension, so we'd end up looking like this, but then surface tension pulls it up to make it look like this, but then we get more pulling up, and we get more pulling up, and we end up having this whole meniscus rising up inside the capillary. Okay, so the adhesive forces are pulling this up. The thing is, this is dependent on, it's more extreme when you have a thinner capillary. So a thinner capillary, a smaller capillary, means increased height of the meniscus. And this is partially how plants get water up into the highest reaches in trees, especially the highest reaches of their branches. There are other mechanisms, other factors in play, but this is one of them as well. So this is what happens with water. But mercury, oh, sorry about that. I'm not sure why that's drawing. Mercury does the opposite. So mercury is a very strong metal. And its adhesive forces, its attraction to the glass, are much less. Writing extra letters in there. Much less than, or much less than the cohesive forces. I'm not sure what that. I see why. Are much smaller. Try this again, much smaller. But the cohesive forces here are the surface tension. The surface tension and the strong metallic bonds pulling in. So the cohesive forces are very strong. And another way of saying this is that mercury is more attracted to itself than to the glass. And this is the same thing that happens with water, where water on a hydrophobic surface is more attracted to itself. So what happens, if we look at the diagram up above, look at the picture, what happens is there's no attractive forces and everything is trying to pull the mercury down. So when we have the mercury pulling down on itself like that, we have a convex shape. So coming down below here and taking a look at what we have. On the left, we have this convex shape. And anytime we see a convex shape, we know that we have stronger attractions pulling in. And so we have stronger cohesive forces. And anytime we see a concave shape, concave pushing up, remember this is relative to gravity, we know that we have forces that are pulling that liquid up. The liquid is being attracted to the surface, to the material that's making up its surface. And so we have stronger adhesive forces. Okay, so homework tonight, we'll have a lot of terminology that is going to come from here. So please make sure you understand. And I will see you in class.